Okay, so our first speaker is Nies, who is going to talk about random sequences of quantum bits.
Right, thank you. I'm quite honored to be invited to this meeting and even kicking it off with this talk on interactions between algorithmic randomness and quantum information theory. So there are various works I'm covering in this talk. The whole thing started off with work with the mathematical physicists Volker Scholz, and Marco Tommo Michael is also in quantum information theory. Tejas Bosraj was a PhD student of Joe who finished last year, and I will cover quite a bit of his results because they naturally continue the work, especially I did with Volker, and often superseded it. So it's my pleasure to include that research. So let's start out by, well, some general observation. How about studying Martin-Löf randomness for objects other than infinite bit sequences or reals? Well, the most common approach would be to not take Cantor space, but rather something else. Heurup and Rogers in 2009 introduced a general framework of computable probability spaces, and that works here. One example is the continuous functions on 0, 1s, one that vanish at 0. The Wiener measure is makes this a computable probability space, and nice results have been obtained by Fouché and then Kjos Hansen and Roth and so on about to what extent classic results hold effectively, meaning well, they hold for Martin-Löf random functions such as iterated logarithm and so on. It's easy to adapt the notion of Martin-Löf test to this setting. Comes out of the natural definition of computable probability space, which includes a notion of effective sigma 1 set. And in fact, there's some isomorphism with the unit interval, which makes it even easier. That's an interesting approach, but not the one I'm following here. I actually want to extend Cantor space, so abandon just bit sequences, but look at things more general than bit sequences, and take a setting where it's also possible to define Martin-Löf tests. Now, for the usual bit sequences, there shouldn't be a new notion. The new notion of Martin-Löf randomness should simply coincide with the previous one. So the main topic following the second approach is to study randomness for infinite sequences of qubits, quantum bits. That was the idea Volker and I had. What happens if you replace bits by qubits? And if you know some quantum mechanics, you can't just list qubits, put them next to each other. They will be entangled. And so the notion of sequence is actually a complicated notion, not just one by one. That's not physically sensible. So the mathematical model of such sequences is the set of states on a certain C-star algebra, M infinity, a well-known C-star algebra. And I'll explain that. Once that's settled, you can define Martin-Löf tests, and indeed, they are equivalent to the usual tests for classical sequences. So Tejas, as I said, wrote a thesis extending this work that appeared in the Journal of Mathematical Physics and adding a lot of depth to it in this thesis, and it goes along with 2 journal papers and 1 conference containing the main results. So a bit of an idea what these sequences of qubits are. Well, what's a qubit? A physical system that can be in 2 classical states, like electrons spin up, spin down, spin half particles, and the spin can be up and down. So the system of n qubits is modeled by a vector in 2 to the n dimensional Hilbert space. So that's huge, and that's really what gives the power of quantum computation, that just n qubits can in some sense look at all the configurations of n classical bits, all the 2 to the n possibilities in a superposition. That's what makes Shor's algorithm and so on work. So, but they can be entangled. So if I delete one, then usually the remaining ones will be in a superposition of possibilities. Detail to follow. Such a superposition is modeled by a density matrix, which is a concept introduced by von Neumann. It's the matrix of that size here, Hermitian, all eigenvalues positive, and their sum is 1. That's the density matrix, the fundamental notion of quantum mechanics and information theory. So what's the state? And is an infinite sequence of such density matrices, so that deleting the last qubit of row n plus 1 gives row n. Just like for a classical sequence, but deleting is actually a complicated process, and some detail will be needed there. Luckily, there's a simple case, which I will do first, namely, all the matrices are diagonal. So if you read this definition for diagonal matrices, well, it just gives 2 to the n eigenvalues, their sum is 1, and they're all positive. So that's a measure on 2 to the n objects, say strings of length n. And the coherence makes the whole state then a measure on Cantor space simply. And that's a statistical superposition of classical infinite bit sequences. So that case is easier, and therefore I want to treat it first. Normally, well, in previous talks, I did quantum first, and there were so many definitions that people pretty much lost me. So to avoid this, I want to do the measure case first, and that's its own paper now, joined with Frank. Stefan has just appeared this year. And so I talk about Martin-Löf absolutely continuous measure. I don't say Martin-Löf random measures because this is not really a randomness notion as you expect. For instance, a computable measure can be absolutely, Martin-Löf absolutely continuous. All right. So for those who don't remember, what's the Martin-Löf test? What's Martin-Löf random? Let lambda be the uniform product measure, or Lebesgue measure, as some people say, gives 0 and 1 the same probability on Cantor space, this thing here. A nice compact disconnected space of infinite bit sequences. The Martin-Löf test is a uniformly sigma 1 sequence of course, open sets. The mth set has measured at most 2 to the minus n. And to be Martin-Löf random means passing each Martin-Löf test, which means that sequence Z is only in finitely many of those UNs. These guys try to approximate Z, get smaller and smaller, but eventually they can't because Z is random. That's perhaps the idea Martin-Löf had. He also had some motivation from statistics. That's how the notion came about, and it's still the most studied and perhaps most well-known randomness notion. One bonus for this notion is that it can be described finitarily by just looking at the initial segments. K of x is the length of the shortest prefix free description of a binary string, sorry, x here, string x. So if z is given and n is a number, z up to n is the initial segment, so the first n bits. Schnorr-Levin says z is Martin-Löf random just if each initial segment is incompressible, meaning random as a finite thing in the sense of k. And technically, you need to add some, introduce some constants. So random means for some constant b, z up to n is not compressible past n minus b. Shannon, quite a bit later, came up with the equivalent condition, which actually says k of z up to n grows beyond n. So it's infinite in the limit, the difference, right? What you think isn't k at most n, k of an n-bit string, but no, it's prefix-free complexity. So we can't just copy the input and write it down. We lose a bit of space to make the machine prefix-free. So in fact, the upper bound is something like n plus, one computable upper bound is n plus 2 log n, and so there's space for this limit to be infinite. All right, so Chaitin's condition is what we later will generalize in the measures and also quantum setting. So here's now my definition. If you forgot, a measure is absolutely continuous if every lambda null set is also mu null. And now we want to just talk about Martin-Löf null sets, and that makes Martin-Löf absolutely continuous. So in detail, I want that for any Martin-Löf test GM, mu of GM, the infimum of these values is 0. Why not limit? Yeah, you can say limit, as I'll tell you shortly. So example, the uniform measure is MLAC because it's trivial, so that's computable, of course. If I take a positive sum of Dirac measures, so convex sum, you could say, call this mu, then mu is MLAC just if each of the Z case is Martin-Löf random. Left to right is trivial here, but right to left needs a little work. That's all in the paper with Frank. In particular, we've got nothing new for the classical bit sequences, identifying a sequence with this Dirac measure that concentrates on that sequence. So that's the main definition for the first part. Any questions? Chat is possible. No? Okay. Here's the definition again. And as I said, you can, well, take the limit instead of the inf, because each Martin-Löf test can be replaced by a descending Martin-Löf test, namely the union of the components greater than m, replacing dm. So that's a descending test now, and there the limit would be 0 because that's mu is a measure. And since there's a universal Martin-Löf test, mu is MLIC simply means mu of non-MLR is 0. Each AC measure is MLAC, so it's weaker than absolutely continuous, which is not an effective notion. So another well-known test notion, which for bit sequences is equivalent to Martin-Löf tests, is the Solvent test. Again, a sequence of uniformly sigma 1 sets, but this time we only ask the sum of their measures is finite. So mu passes the test if the lim of mu of sk is 0. So think of the Borel-Cantelli lemma, which says that if these are events, the chance of being infinitely often in them is 0. Right? So for bit sequences, it just says that eventually the sequence is not in sk. For measures, now we get this condition. The lim of mu of sk is 0. It's easy to see that mu is MLAC just if mu passes each Solvent test. Why is that? Well, Solvent tests are more general, so right to left is trivial, but for left to right, well, take the class of bit sequences that occur in infinitely many of the SKs. We know Solvent and Martin-Löf are equivalent for bit sequences, so this class V only consists of non-Martin-Löf random sequences. Okay, great. What's that help us? Well, mu of V is 0, but Fatou's lemma says the lim sub of the mu of sk is less than mu of V. And therefore, the lim sub must be 0, and hence the limit. So that's all. It's quite simple. In the quantum setting, it's a theorem, actually, the equivalence by Tejas. Okay, so what Frank and I did next was look at analogs of the Schnorr-Levin theorem. And what comes to mind is to average out k over the strings of length n. And that's k of mu up to n. So that's what this formula says. The mu weighted average of the k of x over all strings of length n. Of course, this doesn't tell you how to describe mu up to n. It sort of gives you an idea how the complicated and simple strings are weighted under mu. For the uniform measure lambda, we get a maximal k value, namely n plus k of n. This funny plus here always means up to an additive constant. And we also found another example of a different example of a measure with maximum k complexity, also computable, by the way. So it seems to say the measure is disordered. There's no structure in it. That's one possibility to be MLAC. Now, sadly, this notion doesn't do Levin-Schnorr. Both implications of Levin-Schnorr fail. Well, some weaker things hold though, so it's not entirely useless. For the first non-implication, so mu in MLAC doesn't imply the initial segments are k incompressible. Well, we make an MLAC measure, call it mu again, so that for each theta, k of mu up to n is actually less than, oops, this one here. For instance, n minus square root n is possible. And 1 minus epsilon n is not possible, by the way. So that's sort of as good as it gets. Well, mu is a convex sum of Dirac measures for Martin-Löf randoms, which makes it random, MLAC, I mean, and we make the z case to have very long initial segments of zeros, and that presses down k of mu up to n. Now the other non-implication, we just proved something on bit sequences. We made 2 bit sequences, x and y, so that the average of the Dirac measures for those 2 sequences works as the counterexample. So how do we do that? Make x and y so that y is not ML random, and the sum of the initial segment complexities is at least 2n, all up to a constant, which of course means k of mu up to n is at least n up to a constant. But since y is not Martin-Löf random, mu is also not MLAC. So near the end of the paper, we summarized the various so-called randomness notions for mu, and there's quite a bit I haven't mentioned here. Let's look at the top line. These are the strongest notions. Just AC is, well, in some sense, says mu is unstructured, so let's include it. And here, maximum k complexity, such as lambda. And here's one that I haven't mentioned yet. So what's P? P is the uniform measure on the space of probability measures. Remember the Heuer-Rocher setting, all probability measures on Cantor space form a nice computable probability space, where P is the uniform measure. It's the obvious definition of P, but I won't give it here. This has been studied in Calver's thesis from under Peter Czolak, probably 10 years back, or a bit less. And he showed that if mu is MLR with respect to P, then mu is actually orthogonal to lambda. So some lambda null set is a mu co-null set. And that means, of course, it's not AC. Right? So these 2 top notions exclude each other. This one is pretty interesting. You could call it Kolmogorov random. Infinity often C is maximal. We showed that one implies MLAC. We don't know if it implies MLAC relative to 0 prime. And the last is some variant of Bruno's theorem, really. It says that if mu is MLAC, then C of mu n is actually close to n in that sense. So we managed to prove that implication. All the implications in the central column are proper via Dirac measures as counterexamples. Any comment or question on this diagram? Okay, if not, I want to tell you about QK, which is from Tejas's TCS paper. QK is quantum K, but there are many quantum versions of Kolmogorov complexity. This is one that works in our setting. I first do the measure version. We noted k is a bit unsatisfying. It doesn't do Schnorr 11. So how about this? Take a measure on the strings of length n, call it alpha. And it's the length of alpha in a sense. Qk epsilon of a, so we now have a positive, say, rational epsilon as a parameter, is the minimum of all values k of f plus log size f, where f is a set of n-bit strings and alpha of f is greater than epsilon. So this is the problem of finding a set of strings where the measure is larger than epsilon. How complex is that? So that's qk epsilon. K of f is simply describing f, say, as a string of length 2n times n. That's easy. What about this one? Well, of course, if I make the set f super large, it's easy, right? It gets trivial even, but they want to put a penalty on two large sets f. So logarithm of size f is that penalty. The larger f gets, the worse. Now letting f equal all strings of length n, that's what I mean by this expression. Pretty awful, but yeah, whatever. Then I get the maximum upper bound, k of n plus a constant depending on epsilon. That's great. And if alpha concentrates on a string sigma, quick calculation shows that I get a minimum. So I just get k of sigma, what I had before. So after Bottrach, who did this in the quantum setting, one can show a measure mu passes all restricted Solvent tests just for each epsilon the changing condition holds, namely lim and qk epsilon of mu up to n diverges away from n. And restricted means that I don't have arbitrary sigma 1 sets, I need to have Clopen sets and list those effectively. It doesn't make the least of a difference for bit sequences, but for measures it probably does. And it doesn't for bit sequences because the sequence has to choose one interval in the sigma 1 set, and so you can just list them separately. But that argument doesn't work for measures. So if we want these restricted Solvent tests, then we have a nice characterization in terms of qk. All right, I promised also the Shannon Macmillan Brahmin theorem. I'm not sure I have a lot of time for that, but briefly, so you know what the shift operator is and shift invariant and hopefully ergodic. The shift invariant measure is ergodic if, well, say, for each row integrable function f times t is equal to f. For each shift invariant function, the integral is constant. Oh my God, it's late in New Zealand, it's past 9. Sorry for the short lapse. So each such function is constant row almost surely. For sets, it says an invariant set is null or co-null. That's actually enough. For such measures, we can define the entropy as the limit of the entropies at finite levels, weighted by n. So it's this familiar expression, hn of rho is -1 over n weighted log value of the row. So this measures the surprisal, in some sense, the unexpectedness of the measure. And h of lambda is 1, and that's the maximum possible value. Smb theorem tells you how to get this entropy value by just looking at one arbitrary path or random path. So it says, well, define the empirical entropy along z as this value, -1 over n, log of rho of z up to n. So that hn of rho is the rho expectation of that empirical entropy normalized to the length. Smb says if rho is ergodic, then for rho almost every z, the lim of these empirical entropies is h of rho. And in applied sciences, people often actually care about finding that entropy, and this gives them a way to experimentally actually find the entropy. Just do random samples and calculate this, and eventually you must get close to the actual entropy. In fact, in fields such as signal processing and econometrics, these measures are called ergodic. The abstract definition of ergodic is not good for them, and they just want this property, and perhaps a slight generalization. So the algorithmic version of this theorem says if rho is computable, then the conclusion holds for rho ML random Z. Ruckman, the ergodic theorist, proved this implicitly in 2009, and Heurup came up with an explicit nice proof using the Birkhoff's theorem, I think. So that's, and we ask now, how about for measures? Can I replace that Z, that path, by a measure that's MLAC relative to rho? Which means, of course, the same definition, but for each rho ML test, like this. And the answer is yes, but we need one extra condition. Namely, we need that the empirical entropies are bounded by some constant. Also doesn't work. So if Hn rho is below some fixed d for each n and each row, each n and each input z, then if mu is MLAC with respect to rho, then the lim of a mu Hn rho is h of rho, where this is simply the mu average of these values, which if mu is Dirac collapses to the previous, namely the empirical entropy along a path. So that also follows easily from this time the dominated convergence theorem, which is why we need that constant d here. Okay, and we show the boundedness condition is necessary. So now I have to go right away to the quantum part of my talk, and it needs a few definitions, which hopefully won't throw you. What's a quantum bit? Well, it's a physical system that has two classical states, and the actual state is the superposition in terms of complex numbers whose length is squared sum up to 1. If I measure with what's called a standard basis, namely 0 and 1, I get, in those funny Dirac half brackets, I get 0 with probability alpha length squared and 1 with probability beta, okay, absolute value is better, squared. And now to do n qubits, we take the tensor power of C cross C. And that simply is the 2 to the n dimensional Hilbert space. I write tensor because in quantum physics, tensor means combining two systems. So that's combining the system consisting of n qubits. The standard basis of that Hilbert space is given by n-bit strings. It consists of those vectors, A1, tensor, and so on, AN. And the state of n qubits, is represented by a unit vector in that space. It's a linear superposition of the base vectors. And an example is the EPR state, as physicists call it. So it's considered two photons that are entangled. They could be far apart now, but they're still entangled. And their common state is this EPR state, namely it's 1 over square root 2, both are 0, plus 1 over square root 2, both are 1. The vector is there to make it a unit vector. So there are pure and mixed states. Pure state is just a unit vector, and physicists actually like operators more than vectors. So the Dirac notation, this thing here, which many people hate, is actually just the orthogonal projection onto the subspace spanned by psi as a vector and fixing psi. So it's just that, make psi an operator. And our mixed state is a convex linear combination of such objects by where the pure states in there are pairwise orthogonal. So that's really the same as the density matrix, where the pi's are the eigenvalues. To define it as operator, we remember the trace is the sum of the eigenvalues, and then the mixed state is just a Hermitian operator S on the tensor power, having trace 1 and no negative eigenvalue. So as a matrix, it's just a density matrix. Sorry, was too short. So the eigenvalues sort of give a measure on those eigenvectors, their sum has to be 1 and they're all non-negative. And now this set of notions allows us to define what it means to delete the last qubit. I told you already that's a problem. Just take the EPR state. If you delete one photon, so to speak, then the other, which was entangled with the first, doesn't know what it is anymore. It can be anything. So it's just this statistical superposition of the two possibilities, 0 and 1. So to make this mathematical, well, we call M2n is the C-star algebra of 2 to the n by 2 to the n matrices. And now to make this coherent with our idea of measure on Cantor space, we index the entries not by numbers, but by pairs of strings of n bits, thinking of them as giving the reverse binary representation of a number, such as here. This is 5, 7, reading the number from the left, and we don't want the leading one. So, and now it's easy to define the partial trace given the matrix in M 2 to the n plus 1. So we have two. Well, we have entries are written like this. If Tn of m, the partial trace, is the 2 to the n by 2 to the n matrix, where you just take the sum of corresponding components in the left upper and lower, right lower quadrant. Something like this. Oh, no, it's not working. Good luck. Try. Yeah. So I want, here's a, how was it? A sigma 0 tau 0, and here is in the same position a sigma 1 tau 1, because 1 is the last digit is the most significant. And I just want to add these together to get B sigma tau here. So the matrix is a quarter as big only. Hope that helps. And now if it's a fundamental operation in all the quantum physics books, so I dwell a bit on it. Again, for the EPR state, I take the pure state, and if I, as they say, trace out the second qubit, I get this thing here, totally mixed state, which is what's left of the system after I delete one of the entangled photons. If the states are measures, it's quite simple. I just have the diagonal and have to add corresponding elements. And by our indexing via strings, it simply gives the measure on n bit strings induced by alpha, where alpha is the measure on n plus 1 bit strings by this obvious equation. So that's all it does. And that's why if I have coherent sequences of density matrices in the diagonal case, I just get a measure. So quantum Cantor space, which is actually a nice space which is connected and has convex structure, but I won't go into that. So it consists of the coherent sequences of density matrices, namely Tn of rho n plus 1 is rho n for each n. And that's the same as the states on the what people call the CAR algebra, which is some kind of direct limit of the matrix algebras, and with the closure under norm. Diagonal states correspond to measures, as I've explained already. The Lebesgue measure is now called a tracial state, which is just the diagonals times 2 to the minus n. A classical bit sequence is the Dirac measure concentrated on that sequence. So in that way, the Cantor space can be embedded into the quantum Cantor space. So all this is not really new. not at all. It's been studied back to the 1980s in different guises. And in mathematical physics, it goes under quantum spin lattices or the like. And here's the case of one-dimensional quantum spin systems. Peter Nikens has just written 5 years ago a textbook on this. And the dynamics was studied by Belakovic and 3 others in an Inventiones paper. Right, just like for sequences, you can delete the first qubit and you get a nice dynamics. And in fact, they had a quantum version of the Shannon Macmillan theorem, but not effective. So I'll tell you a bit if time permits. So all this is just about sequences, and now we need the randomness tests for states. One problem is that, well, we can't really compute with complex numbers, at least not with classical Turing machines, and so we only want algebraic complex numbers. Clopin sets become special projections. So special projection is a Hermitian matrix where the entry, that's the projection and the entries are in algebraic. This is just the same as a subspace, but it's easier to use the language of projections. An expression that comes up often and somehow connected to Born's rule in quantum mechanics is take the trace of eta p, where eta is a density matrix, and p a projection on the same matrix algebra. So this is, in some sense, the expected square length of projecting eta onto the space corresponding to p. If eta is just a vector, it's really dead. It's just the inner product of v and p of v. And in general, it's the statistical superposition of those. That's why I wrote expected length. If eta is a measure and p is classical, so just a set of strings or Clopin set, then I simply get what the measure gives to p, which is what I wanted. So trace of eta p is in some sense measuring eta with p. And now to define my quantum Martin-Löf tests, first note we can embed m2 to the n into m2 to the n plus 1 in the obvious way by copying. And so I can compare projections in different matrix algebras by this embedding. P less than equal to q simply means that the range of p is contained in the range of q, which is the subspaces. All right, and now I can define sigma 1 probabilistic sets on the space as computable ascending sequences of special projections. Just like a classical sigma 1 set is an ascending sequence of Clopin sets in a computable way. If eta is a state, then g of eta will be the soup of these things measuring eta with pn. So it's the soup of that expression. And if rho is the tracial state, remember that's what a tracial state is, then g of tau is simply soup 2 to the minus n trace of pn, because that's all that's left of the expression. And instead of g of tau, one could also write tau of g, because tau is like a measure applied to g. We use that more frequently, but really to stress the set aspect of g, I want to write g of tau. So a quantum Martin-Löf test now finally is an effective sequence gr of quantum sigma 1 sets, so that tau of gr is at most 2 to the minus r. So just like in classical, but replacing the sigma 1 by quantum sigma 1 probabilistic sets. And the state rho now passes the test if inf gr of rho is 0. That's the definition that works. It took us a while to find it, but it's given by, it's supported by robustness properties and nice applications. So again, you can think of the asymptotic measured value at rho as this infimum. That's the intuition. And of course, quantum ML random means to pass each quantum ML test. We showed there's a universal test and that every ML random bit sequence is quantum ML random, as we want. More generally, as Tejas Bojar showed, if a measure is rho is MLAC, then rho is quantum ML random. That means for measures, I don't have a new notion. I have the same notion MLAC as studied already. That's great. So what can we do with this? Well, first about the equivalence with with Solvent tests. Well, define quantum Solvent tests as expected. And now remember we had restricted Solvent tests already where all the components were clopin. And now we say restricted means all the components are projections that are effectively given. So it's not a limiting thing, it's just one each time. Given those test notions, we have quantum Solvent random and weakly quantum Solvent random as expected. And in Tejas' thesis and JMP paper, it says quantum ML random is equivalent to quantum Solvent random, which is nice and shows it's robust and also shows that the QML states are convex. For that, you need the Solvent definition. Okay, so yeah, I may need a few more minutes, but let's see how things go. QK also makes sense in the quantum setting. Given the time is advanced, I skipped the precise definition, but that's what they really had in Tejas and well, in co-work with Joe, the supervisor. So here's the definition of QK with parameter epsilon of alpha. It's really the same thing, except that F is now a subspace and size F means the dimension of F. So a special projection. And alpha of F greater epsilon becomes the same expression here, trace alpha P is greater than epsilon. And Bojras proved, and it's not actually that hard, this one, rho passes all restricted Solvent tests just if the lim of QK epsilon of rho n minus n is infinite. Again, we don't know if restricted actually matters. So we don't know if we have an initial segment characterization of QML random. If the states are non-high, then the two notions actually coincide. So you have to work a bit to make a counterexample. Though I believe it does exist. In the Schnorr setting, there's no such problem. Tejas also showed for Schnorr random, quantum Schnorr randomness is equivalent to incompressibility for a restricted version of QK, where one uses those computable measure machines, namely prefix-free machines, and the measure of the domain is computable. So here's a diagram of all the notions considered and their coincidences. So the top is QML random and Q sol random, which trivially implies Q weak Solvent random, which is equivalent to QK incompressible. And down here we have the Schnorr setting. So this is proper, of course, but we don't know if all these things are the same at present. Okay, so I skipped the effective Smb theorem. It's just really the version for states, because there's also a notion of ergodic states, and for computable ergodic states, one wants to guess the entropy in the von Neumann sense. And the conjecture is that if mu is quantum ML random with respect to rho, and also there's a boundedness condition as before, then I get the entropy in this way. We can do it for all cases except when rho is actually a state, not just a measure. Right, so I can't really go into detail. It also settles the IID case, which before we had done separately. So it uses this pinching out of the diagonal, which makes a state into a measure, and that's often useful. Yeah. Okay, finally, I do have time for just alerting you to other results that connect quantum information theory with mathematical logic. And this one has caused quite an uproar. It's actually the latest of a chain of results saying that the spectral gap problem is undecidable, whether a system consisting of finite chains of qubits has a spectral gap in the thermodynamical limit. What's a qubit? It means declassical states. Yeah. So this goes back to the Ising model eventually and the Heisenberg model, of which is the quantum version of that for magnetism. So what you give is local Hamiltonians, and they describe, well, sort of one side external effects on the qubits and also nearest neighbor interactions. And this, by shifting them around, we get a global Hamiltonian given by this formula here, that one. And the question is in the thermodynamical limit, namely if n gets big, is there a spectral gap, which means, well, the difference between the least and the next eigenvalue. So in the finite setting, finite dimensional setting, that's positive, of course, but that's this picture from the Nature paper also of Qubit and others. That's really his name, Qubit. Yeah, written like that. So the question is in the limit a spectral gap or not? And the latest version, which used one-dimensional system rather than, well, it's used chains rather than square configurations, but still a large number of classical states. So what they did, given a Turing machine M, they compute local Hamiltonians so that if the machine halts on an input, then the Hamiltonians for this input give a sequence that's gapless, and otherwise the sequence is gapped. So that shocked some physicists whose main work seems to be to determine if a particular system is gapped or not. So that's for particular systems a hard question, and the result says it's undecidable in general. Of course, you wonder, are there connections to what I told you before, to this infinite sequences of qubits? This is finite, but just getting big. But I think people have tried to find a setting where the systems are actually infinite, and one would have to look into that to find connections. Of course, the language is foreign to me, so I haven't been successful in that yet, but who knows. And here are a couple of references, and that's it. Thanks for attending.
Okay, thank you very much for your talk. So is there any question in the audience?
I was wondering if there's a result like Stephan's that says that, for example, there's a pi0n class all of random qubits or something like that.
Well, the problem is you can't just make classes because they are not paths on a tree. But the fact that there's a universal quantum Martin-Löf test gives a result of that kind. Yes, that there's in some sense a quantum pi0n class containing only Martin-Löf random qubit sequences.
Can you remind me what the universal test looks like? I forgot. I'm sorry.
Peter, it's just we just took the earliest construction of a universal test, not using Kolmogorov complexity, but just throwing things together. List all the Martin-Löf tests, and then take a diagonal union, making sure the indices shift so that the measure isn't too large. So something like that worked in the quantum setting, though we had to be more careful what it means to take finite unions of projections. So it's all explained in the paper, in the 2019 paper, in the JMP. So I don't think I can write it down. It would take too long right now, but
thank you very much.
It's what you would think it is in the quantum setting.
Okay, thank you. Any other question?
Probably very unrelated, but what do you think about this claim result about the RE versus MIP star? You know, these entangled multiprovers that supposedly capture all computable enumerable languages. Any
Yeah, so that she's
Any
talking about.
opinion of whether it is correct or whether it is important?
Okay, I know a bit of operator algebras, and I know the paper that shows zero-sums conjecture as equivalent to for Neumann's, sorry, to the Kohn conjecture. So I know a bit of the background. Actually, Scholz is on that paper, so he told me about it early on. And well, I haven't studied enough detail to make my own opinion. But I think just on generally the people on the paper are all very serious and successful researchers such as Wittig and Jen Feng and Sydney and so on. And also nobody has found a mistake in the year that has passed so far. So I think it might quite likely be correct.
Thank you. Any last question? We're a bit off topic. Oh, of time. No, so let's thank the speaker again.
Thank you.